One factor between subjects, ANOVA. This section shows how ANOVA can be used to analyze a one-factor between subjects design. The null hypothesis tested by ANOVA is that the population means for all conditions are the same. This can be expressed as HO is mu1 equals mu2 ... equals mu k, where HO is the null hypothesis and k is the number of conditions. If the null hypothesis is rejected, then it can be concluded that at least one of the population means is different from at least one other population mean. We will use the Smiles and Leniency case study as our main example of how to conduct a one-factor between subjects ANOVA. In this study, there were 4 conditions with 34 subjects in each condition. There was 1 score per subject. In the Smiles and Leniency study, the null hypothesis is mu false equals mu felt equals mu miserable equals mu neutral. Analysis of variance is a method for testing differences among means by analyzing variance. The test is based on 2 estimates of the population variance, sigma squared. One estimate is called the mean square error, MSE, and is based on differences among scores within the groups. MSE estimates sigma squared regardless of whether the population means are equal. The second estimate is called the mean square between, MSB, and is based on differences among the sample means. MSB only estimates the variance if the population means are equal. If the population means are not equal, then MSB estimates a quantity larger than the variance. Therefore, if the MSB is larger than the MSE, then the population means are unlikely to be equal. On the other hand, if the MSB is about the same as MSE, then the data are consistent with the hypothesis that the population means are equal. Before proceeding with the calculations of MSE and MSB, it is important to consider the assumptions made by ANOVA. The first assumption is that the populations have the same variance. This assumption is called the assumption of homogeneity of variance. The second assumption is that the populations are normally distributed. The third assumption is that each value is sampled independently from each other value. This assumption requires that each subject provide only one value. If a subject provides 2 scores, then the values are not independent. The analysis of data with 2 scores per subject is shown in the section on within subjects ANOVA in this chapter. These assumptions are the same as at test for the difference between independent groups, except that they apply to 2 or more groups, not just 2 groups. The means and variances of the 4 groups in the Smiles and Leniency case study are shown in this table. Remember that there are 34 subjects in each of the 4 conditions: false, felt, miserable, and neutral. We will now use the data in this table to describe some ANOVA calculations. The first calculations in this section all assume that there is an equal number of observations in each group. We will refer to the number of observations in each group as lowercase n and the total number of observations as uppercase N. For these data, there are 4 groups of 34 observations. Therefore, lowercase n equals 34 and uppercase N equals 136. Recall that the assumption of homogeneity of variance states that the variance within each of the populations is the same. This variance is the quantity estimated by MSE and is computed as the mean of the sample variances. For these data, the MSE is equal to 2.6489. The formula for MSB is based on the fact that the variance of the sampling distribution of the mean is sigma squared divided by n, where n is the sample size. Therefore, if we knew the variance of the sampling distribution of the mean, we could compute sigma squared by multiplying by n. Although we do not know the variance of the sampling distribution of the mean, we can estimate it with the variance of the sample means. For the Smiles and Leniency data, the variance of the 4 sample means is 0.270. To estimate sigma squared, we multiply the variance of the sample means, 0.27, by n, the number of the observations in each group, which is 34. We find that MSB is equal to 9.18. Rearranging this formula, we can see that the variance is n times the variance of the sampling distribution of the mean. Therefore, if we knew the variance of the sampling distribution of the mean, we could compute the variance by multiplying the variance of the sampling distribution of the mean by n. Although we do not know the variance of the sampling distribution of the mean, we can estimate it with the variance of the sample means. For the Smiles and Leniency data, the variance of the 4 sample means is 0.27. To estimate the population variance, we multiply the variance of the sample means, 0.27, by n, the number of the observations in each group, which is 34. We find that MSB equals 9.18. Here we sum up the steps for computing the MSB with equal sample sizes per condition. First, we compute the mean of each condition, then we compute the variance of these means. Finally, we multiply the variance of the means by n. If the population means are equal, then both MSE and MSB are estimates of the population variance and should therefore be about the same. Naturally, they will not be exactly the same since they are just estimates and are based on different aspects of the data. The MSB is computed from the sample means, and the MSE is computed from the sample variances. If the population means are not equal, then MSE will still estimate the population variance because differences in population means do not affect variances within the groups. However, differences in population means affect the MSB since differences among population means will tend to produce differences among sample means. It follows that the larger the differences among sample means, the larger the MSB. In short, the MSE estimates the population variance whether or not the population means are equal, whereas the MSB estimates the population variance only when the population means are equal and estimates a larger quantity when they are not equal. The critical step in ANOVA is comparing MSE and MSB. Since MSB estimates a larger quantity than MSE only when the population means are not equal, a finding for a larger MSB than an MSE is a sign that the population means are not equal. But since MSB could be larger than MSE by chance even if the population means are equal, MSB must be larger than MSE in order to justify the conclusion that the population means differ. But how much larger must MS be? For the Smiles and Leniency data, the MSB and MSE are 9.179 and 2.649 respectively. Is that difference big enough? To answer, we would need to know the probability of getting this big of a difference or a bigger difference if the population means were all equal. The mathematics necessary to answer this question were worked out by the statistician R. Fisher. Although Fisher's original formulation took a slightly different form, the standard method for determining the probability is based on the ratio of MSB to MSE. This ratio is named after Fisher and is called the F ratio. For these data, the F ratio is 9.179 divided by 2.649, which equals to be 3.465. Therefore, the MSB is 3.465 times larger than the MSE. Would an F ratio as large as the F of 3.465 that we just calculated have been likely to have happened if all the population means were equal? That depends on the sample size. With a small sample size, it would not be too surprising because small samples are unreliable. However, with a very large sample, the MSB and MSE are almost always about the same, and an F ratio of 3.465 or larger would be very unusual. The figure shows the sampling distribution of F for the sample size in the SMILES and leniency data. You can see that F ratios of 3.465 or greater are unusual occurrences. The area to the right of 3.465 represents the probability of an F that large or larger and is equal to 0.018. In other words, given the null hypothesis that all the population means are equal, the probability value is 0.018. This p-value is below 0.05, so the null hypothesis can be rejected. Therefore, the conclusion that at least one of the population means is different from at least one of the others is justified. As stated previously, the shape of the F distribution depends on the sample size. More precisely, it depends on two degrees of freedom parameters, one of the numerator, MSB, and one for the denominator, MSE. Recall that the degrees of freedom for an estimate of variance is equal to the number of the scores minus 1. Since the MSB is the variance of k means, it has k minus 1 degrees of freedom. The MSE is an average of k variances, each with n minus 1 degrees of freedom. Therefore, the degrees of freedom for MSE is k times n minus 1, which equals capital N minus k, where n is the total number of the scores, n is the number of each group, and k is the number of the groups. For the SMILES and leniency data, df numerator is k minus 1, which is 4 minus 1, which equals to 3. df denominator equals capital N minus k, which is 136 minus 4, which equals to be 132. We previously calculated that capital F equals 3.465. Using the F distribution calculator that can be found in the calculator section, we can find that P equals 0.018. Is the probability value from an F ratio a one-tailed or a two-tailed probability? In the literal sense, it is a one-tailed probability because you can see in the figure. The probability is the area of the right-hand tail of the distribution. However, the F ratio is sensitive to any pattern of differences among means. It is therefore a test of a two-tailed hypothesis and is best considered a two-tailed test. Because ANOVA and an independent group's t-test can both test the difference between two means, you might be wondering which one to use. Fortunately, it does not matter since the results will always be the same. When there are only two groups, the following relationship between f and t will always hold: f in terms of 1 and dfd equals t squared times quantity of df, where dfd is the degrees of freedom for the denominator of the f test and df is the degrees of freedom for the t test. dfd will always equal df. Why do scores in an experiment differ from one another? Consider the scores of two subjects in the smiles and leniency study. One from the false smile condition and one from the felt smile condition. An obvious possible reason that the scores could differ is that the subjects were treated differently. They were in different conditions and saw different stimuli. A second reason is that two subjects may have differed with regard to their tendency to judge people leniently. A third is that perhaps one of the subjects was in a bad mood after receiving a low grade on a test. You can imagine that there are innumerable other reasons why the scores of the two subjects could differ. All of these reasons, except the first, that subjects were treated differently, are possibilities that were not under experimental investigation, and therefore all differences or variation due to these possibilities are unexplained. It is traditional to call unexplained variance error, even though there is no implication that an error was made. Therefore, the variation in this experiment can be thought of as being either variation due to the condition the subject was in or due to error. The sum total of all reasons subject scored could differ that were not measured. One of the important characteristics of ANOVA is that it partitions the variation into its various sources. In ANOVA, the term sums of squares is used to indicate variation. The total variation is defined as the sum of squared differences from the mean of all subjects. The mean of all subjects is called the grand mean and is designated as GM. When there is an equal number of subjects in each condition, the grand mean is the mean of the condition means. The formula for the total sum of squares, or sum of squares total, is shown here. This formula says to take each score, subtract the grand mean from it, square the difference, and then sum up these squared values. For the smiles and leniency study, SST equals 377.19. The formula for the sum of squared between SSB, or the sum of the squares condition, is shown here. In this formula, n is the number of scores in each group, k is the number of groups, m sub 1 is the mean of condition, m sub 2 is the mean of condition 2, and m sub k is the mean of condition k. For the smiles and leniency study, there are 34 subjects in each condition, and the grand mean is 4.83. The SSB is calculated as shown and is equal to 27.5. If there are unequal sample sizes, use this formula to calculate the sum of scores condition where n sub I is the sample size of the ith condition. SST is computed the same way shown previously. The sum of squares error, SSE, is the sum of the squared deviations of each score from its group mean. Xi sub 1 is the ith score in group 1, and m sub 1 is the mean group of 1. X sub I2 is the ith score in group 2, and m sub 2 is the mean for group 2, and etc. For the smiles and leniency study, the means are 5.37, 4.91, 4.91, and 4.12. The SSE is therefore the sum of the squared deviations of each value in the first condition minus 5.37 plus the sum of the squared deviation of each value in the second condition minus 4.91 plus the sum of the squared deviations of each value in the third condition minus 4.91 plus the sum of the squared deviation of each value in the fourth condition minus 4.12. The sum of squares error for this data is equal to 349.66. The sum of squares error can also be computed by subtraction. SSQ error equals SSQ total minus SSQ condition. So, for the smiles and leniency data, SSQ error equals 377.19 minus 27.53, which equals to be 349.66. Therefore, the total sum of squares of 377.19 can be partitioned into SSQ condition, which is 27.53, and SSQ error, which is 349.66. Once the sum of the squares have been computed, the mean squares, MSB and MSE, can be easily computed. The formulas are MSB equals SSB over DFN, where DFN is the degrees of freedom numerator and is equal to k minus 1. For the smalls and leniency data, MSB equals 27.5 over 3, which equals to be 9.17. Similarly, MSE equals SSE over DFD, where DFD is the degrees of freedom of the denominator and is equal to n minus k. For the smalls and leniency data, there are 136 total subjects and 4 conditions, so DFD equals 136 minus 4, which equals to be 132. Therefore, for these data, MSE equals 349.66 divided by 132, which equals to be 2.65, which is the same value as obtained previously by calculating the mean of the sample variances, except for rounding error. Note that the DFD are often called the DFE for degrees of freedom error. The analysis of variance summary table is a convenient way to summarize the partitioning of the variance. The first column shows the source of variation. The second column shows the degrees of freedom. The third shows the numbers of squares, and fourth shows the mean squares. The fifth shows the F ratio, and the last shows the probability value. Note that the mean squares are always the sum of squares divided by degrees of freedom. The F and P are relevant only to condition. Although the mean square total could be computed by dividing the sum of squares total by the degrees of freedom, it is generally not of much interest and is omitted here.